It's still morning, right? Yeah, I think it's still morning. Okay, so I'm going to carry on from where I left off yesterday. Just to recap what we did yesterday. So we looked at the laser measurement principle, the idea that we exchange laser beams between satellites and also measure the motion of those satellites with respect to the free-falling test masses. And we also talked about why and the fact that we need to lock those lasers to each other in order to control the optical beat signals that we're measuring the phase of. Okay, so we ended up talking about these three measurements: test mass to spacecraft, spacecraft to spacecraft, and then at the other end of each arm, spacecraft to test mass, and the whole constellation of those measurements. We saw that those were dominated by frequency noise because of the large path length difference between those two lasers. We also saw that there's a large amount of phase noise due to the fact that those spacecraft are relatively noisy platforms. And we looked at what the consequences of all that is in terms of heterodyne interferometry, tracking of the phase of the beat of those two optical frequencies, and how that gives us a measurement in the end. And then we spent, I can't remember how long it was, the last half of the session, looking at the suppression of frequency noise and spacecraft motion by combining these signals on ground, in processing on ground, in something we call time delay interferometry. And we saw in the end then that we could construct effective synthesized photon paths which effectively measure the same common noise, the same frequency noise, such that the difference between those two contains signal but removes this noise. We ended here with this expression, which was a bit of a hand-wavy argument to show how all the contributions can be related to a strain curve for a given source position on the sky, because we have to take into account this TDI transfer function. Today I'm going to try to approach this slightly differently and do a more simplified version of this. This is useful in particular if you're trying to study sources of noise and how they couple through these TDI combinations. If you want to do something else, which is to assess the science performance in terms of strain curves, you can take a slightly simplified approach, and we'll look at that in a moment. So why, obviously, estimating the science performance of a mission or of an observatory is a key thing to be able to do. Often, in most cases, we use something called the signal-to-noise ratio calculations. You've seen these throughout many different talks, I'm sure. They're used as a kind of a proxy for science performance. They don't encapsulate everything, but they capture a lot of features. But other things you might use are the ability to localize sources or the estimation of source parameters. And you might do this not just in terms of a simple noise curve averaged over sky position and polarization, which is effectively static in time. You might do it in terms of things like duty cycle, observation time, and so on. Okay. So let's see, the performance as a function of different source types is often looked at, and also as a function of different observatory properties. These are key features to make sure you're getting the best science out of the thing you're trying to build. So I'm going to try and talk through how we make a plot like this, or at least what the science performance in these kind of plots, what you can get out of that. So encoded in this plot is effectively a signal to noise here in the colors of these tracks. So as the signal tracks in frequency, you accumulate more signal power. Your noise from your instrument is stationary in time, and so you're accumulating more signal to noise. And we'll see how we calculate that so that you can do that yourselves. So the idea then is to start with a simplification. You can go back to that relationship I had before, which included this complexity of TDI. We can effectively assume TDI works and throw that away from the purposes of looking at science performance. That's not really the right thing to do, and it certainly hides some details. But for back of the envelope calculations, it's a useful trick. So you can effectively say that the output of TDI is related to the noise you have in a single link that we talked about yesterday, and given by this transfer function. Okay. And so if you just make that simplification here, you come back to a relationship between the noise in the single link, that's the noise of the optical metrology, and the noise due to force noise on the test mass primarily, related to the observatory the observatory response function, some geometrical factors for averaging and so on, and the arm length. And you can get a strain curve out of this that gives you, in a rather simpler way, a strain curve that you can use for the next calculations. So if you take some simple noise model rather than that complicated one I had before with all of those noise contributions, if you just say, okay, my observatory, my single link measurement is going to be dominated by optical metrology noise, my ability to make those interferometric measurements, maybe at something like 15 picometers per root hertz total by the time you've taken into account all the measurements you need. Maybe with some noise shaping, we talked about that also yesterday, that's usually put in place because you typically at lower frequency can't make these measurements as stable. You start to be driven by things like thermal noise and things like this. The other aspect we need to take, the other part of the recipe, is to look at the force noise acting on a single test mass. That's a number that's typically expressed in a few femtometers per second squared per root hertz. It's an effective acceleration here. We usually also have a relaxation towards lower frequency, and just for the purposes of engineering construction, we also usually have a relaxation to higher frequency, and of course this doesn't matter so much in the end. It doesn't matter at all, in fact, because this is anyway related to this by a 1 over f squared, so the relative weight of this part of the curve is negligible. So remember, we looked at this single link, we looked at this TDI output yesterday, and we saw that in constructing such a term, we had effectively sampled the gravitational wave signal 8 times, albeit with different delays. But if you go to low frequency, where the delay is all the same, okay, for an effect of the effect at very low frequencies, this delay doesn't do anything. Then I've got 8 times the signal. I've sampled the test masses 16 times. And I've sampled the readout noise, my interferometric noise, 8 times. So that's a ratio of 1 signal to 2 test mass to 1 readout, if you consider this as time domain. So if you think of power, so you want to do this in terms of power spectral densities, noise quantities, then that becomes a ratio of 1 signal to 4 test mass to 1 readout, and it's particularly this ratio that's important. So a single link can be expressed as 1 readout power, 1 unit of readout power, and 4 units of test mass power. So that's a lot of assumptions in there, in particular that the test mass force noise is the same on all the test masses, okay? And that doesn't necessarily have to be true. It also assumes that they are uncorrelated, which also doesn't necessarily have to be true. But this is a reasonable approximation to get you to a noise curve easily, because you can plug these numbers in. You can compute the displacement we get from that force noise in the usual way, and so you end up with an effective displacement noise in your single link coming from that acceleration noise or force noise, just related by the frequency squared, or to the power 4 here in power. So those two numbers I put down, one for the optical metrology noise here in blue. Here was a few picometers per root hertz. For the test mass force noise at few femtometers per second squared per root hertz, results in a displacement that looks like this. And remember, there are 4 of those, so there are 2 times that power in linear spectral density here. And so the sum of those two things gives you that yellow curve, this equivalent single link noise curve here. And then you want to relate that to strain using that formula we talked about earlier, and you get the total strain curve then if you include the response over the sky and polarization. So that's the easy recipe to produce such a strain curve. You don't need to go through all of that TDI stuff, although you should if you're doing things properly. Yeah, there's a note here, just that there's in LISA there are, when you construct those TDI variables, you have potentially 2 channels which are quasi-independent, and it remains to be seen how independent depending on the noise correlations. But effectively, then you can say there's another factor of 2 you can get here, because both of those measure the signal, but their noises are to some extent independent, so you increase your signal to noise again. Okay, so if you recall how that relates to this, it looks just the same as we had here. We're force noise limited here, and we're optical metrology limited in this band, so it looks just the same, just rather easier to derive. Okay, so then in doing science performance, you often want to calculate a signal to noise ratio. That's a good proxy for how well will your observatory perform. And it's often expressed in this form here, where the square of the signal to noise ratio is effectively the ratio of the signal power to the noise power integrated over the band of your observation. And there's a link here you can go off and read how you can even derive this. It's done simply using a matched filter or Wiener filter expression. So if you take that then and you want to actually do it in a practical way, if you want to actually do something with that, you need a formulation for what your signal looks like in the frequency domain. We've already seen how to produce this one for the noise. The signal one is often done using in particular for binary signals, it's often done using phenomenological waveforms. I've listed 3 here that I know about at least. I've given you a reference. You can go off and read about one of those. I think it's phenom-C, this reference. And these implementations of these codes return a complex amplitude, okay, as a function of frequency, given some properties of the system, typically the mass ratio of the binary objects in the system, perhaps the total spin, the luminosity distance, and so on. And they are often also sky polarization and inclination averaged in particular. And so when you're using that, and you're using the fact that our strain curve is also sky and polarization averaged, you have to be careful with some of these factors. Okay, remember we had this term here, so this is a practical recipe. This signal waveform, I'm using hand wavy notation here to say that this is averaged over sky position, polarization and inclination, the top line. The bottom line is also averaged, but not over inclination in the case that we've derived it here, but in terms of sky position and polarization. And so if you want a fully averaged SNR, you have to put in some other factors here to make sure that that all comes out right. I've got another reference here. You can go off and look at how these numbers come out. So that's an easy way to do that. We often do this in terms of, we often make these pictures in terms of something called a characteristic strain. It's useful when you're plotting because it represents nicely the area between the curves is related to the SNR that you get. So if you define characteristic strain in these ways for signal and noise and plot those two things, then the signal to noise ratio is related to the area between the two. So here's an example of that, how that looks like. And obviously you can integrate that by eye very easily. I'm sure all of you can do that. So this is 2 × 10⁶ solar mass black holes at redshift 1. If you do the actual calculation and integrate this, you get an SNR around 6,000, and you can hand-wavingly see that that area between those two curves is approximately that size, okay? And this is not quite as, this is not Escher-esque tiling of the space here, but it's roughly of the order, the same order here, okay? So it gives you a by eye estimate of signal to noise ratio. Okay, so that's all I wanted to say on science performance. I'm going to move on to LISA Pathfinder. If there are any questions on that, I'm happy to take them. Otherwise, those references will point you in the right direction if you want to do these calculations yourselves. So, LISA Pathfinder. Who's shouting? Neil. That's right. Yeah, you can play with that. That's right. Maybe I don't know if we can send a link around or something, or we can put it. I can just add it to the slides if you. Yeah. I'll get that off you later. Yeah. Okay. So let's see, LISA Pathfinder. So I'm going to try and talk through a lot of material. I've taken sort of highlights out of the whole mission here. I'm going to talk about what do we test with LISA Pathfinder. I'll try and describe a bit the satellite, the instrumentation, what actually is the science observable that we're interested in this mission. I'll try to give you a hint of how all the operations ran and what kind of experiments we did. We'll see noise sources appearing as I go through all of this, and we'll finish on what did we actually learn and what's the impact of all of that on LISA. So that's quite a lot to get through, but I think we have plenty of time, so we should be good. Okay, so remember, we've seen this curve many times now, and the important part is that this lower frequency, we've said it numerous times, is totally dominated by the force noise on the test mass. So your ability to put a test mass into a free fall that's quiet enough to allow us to resolve the tidal forces caused by gravitational waves. Okay. Now, so that gets us all the way up to these frequencies here, up to millihertz. So this last little bit of the frequency band is metrology limited. So we were aiming in LISA Pathfinder to do this part. This part you can partly do on the ground, and that's a bit the argument here. A lot of this optical metrology is well demonstratable on the ground, apart from the millions of kilometers. Okay, so there are some challenges there to simulate that, but nonetheless, a free-falling test mass is almost impossible to do on the ground at this sort of level. There were attempts to do it with torsion pendula and things like this, but to get down to the level we need here is pretty much impossible to do on the ground. So LISA Pathfinder was envisaged to test this part of the LISA noise curve and shows that we can really build a satellite that allows us to do this. Okay, so we test a lot of the LISA performance budget. We do actually all the relevant local test mass disturbance forces. This is going to be exactly the same as the thing we fly in LISA. It's a slightly different environment, but nonetheless, it's extremely representative what we did in LISA Pathfinder. To some extent, we also tested in LISA Pathfinder local interferometry. That's something that's never been done before. Interferometry between free-falling test masses, okay? So certainly not in space. So that's something also that's tested, even though the interferometry is slightly different, as we'll see. I'll describe that a bit later on. We also tested a lot of other technology, the ability to do drag-free control. Can you take a half-a-ton satellite and make it follow a test mass using micronewton thrusters? Okay, so that's not so trivial. We also demonstrated that we can control the charge on the test mass. I mentioned that yesterday. The fact that the test mass is not touching anything means it does charge up from cosmic rays, and so you have to be able to control the charge because that's a noise source. If we have time, we can talk about that perhaps later. We demonstrated the fact that we could build a satellite where the gravitational field, the gravitational potential of the satellite is sufficiently flat that you don't couple through these sort of force gradients the motion of the satellite as a force on the test mass itself. Okay, so that was controlled to a reasonable level. It also had another big effect, which we'll see later when we talk about the control of the test masses. And we showed that we could build a spacecraft which has an environment, in particular in terms of thermal stability and magnetic cleanliness, that's appropriate for putting a test mass in free fall at this level. All of that was not known and not done before. I'm going to mention only one time here. I'm not going to talk about it more. There was some additional payload items on LISA Pathfinder coming from NASA, where there was a demonstration of an alternative drag-free control scheme, and alternative thrusters were also demonstrated. Okay, so it's always nice to have some movies to keep everybody awake. This is a time lapse of the satellite being placed in the fairing of the rocket and transported across the jungle in French Guiana in Kourou, taken out to the Vega C rocket. Unfortunately, I wasn't there when this happened. I had to do real work instead. But hey, you get to watch the videos. And so they take this out here. The rockets. This is the big firework here. Being prepared by these little munchkins on top. Then they put the fairing, so that's your satellite that's taken 10 years to build, getting strapped on top of a bomb, which keeps the adrenaline flowing a little bit. They lock that down on top of the rocket, and then the rocket's left standing, and they actually just take the building away. Okay, so everybody runs away, and then they remove the building and leave the rocket standing, and then in the blink of an eye, up it goes. That was something, I can't remember, it was in the middle of the night here in Europe, so we had to get up in the night to watch the launch. But that was fun. And then it was gone. That was it. It was really quick. Okay, so December 3rd. So that's really our first step. This is the beginning of what's been a fairly accelerated process on our path to getting a gravitational wave observatory in space. Okay, so after that, then the satellite was went through a few orbit raising maneuvers to get it out to an escape velocity and out towards the Lagrange point 1 here, where it was put in a pretty large orbit around Lagrange point 1 and kept in that configuration over the time of the science operations. So that took a few months. We had an industrial commissioning phase where the engineers who'd built everything switched it all on and made sure things were working. Then we switched over or handed over to science operations here in around the beginning of March in 2016 and did a few months of science operations. We only had 90 days of operations planned, which was a pretty challenging thing to organize and make sure we could do all the experiments we wanted. Turns out we did an extension, but we didn't know that at the start. And then there was the period where the NASA team also commissioned their part of the payload and did some operations as well. So that means that each day of these few months here were packed full of experiments. Okay, so we planned everything in advance, and you know, like all good plans, they don't last very long. But they lasted about 2 weeks here. We managed to do the first 2 weeks without changing plans. But it turns out the thing worked rather better than we'd expected, so we had to adjust all the different experiments and rearrange things a little bit. This shows you a little sneak preview of what it looks like in an operations room. It's not always like this. Thankfully, it was quiet some of the time. But this was a time where we were releasing the test masses. The test masses are gold platinum cubes. They weigh around 2 kilos. And if you launch those on a launcher, you got to make sure you lock them down. Okay, so they were grabbed with something like a kilonewton of force with fingers, and then released in once we were in space. And everybody was very nervous whether we could actually release them. Okay, and so this is a nerve-wracking time where the first test mass was about to be released, and everybody's looking around there and watching screens. We're seeing the telemetry in real time. It's a few seconds delayed, the telemetry from the satellite, because it's far away, but effectively we could watch what was going on. You probably recognize a few people in there. You see a very tired version of me who's been up for days, sitting in the background here, waiting to see what happens. Okay, and then so after this, you know, these initial phases were over, we were down to typically a team of 5 or 6 people in this room every day of the week for those few months doing experiments and looking at the data in real time and replanning everything. Okay, so what did we actually do on LISA Pathfinder, and why is this a little bit different from LISA, but also why is it relevant for LISA? So what we did, we wanted to look at, can we put a test mass in sufficiently quiet freefall, okay? And you cannot measure that with respect to the spacecraft, because the spacecraft is jittering around at nanometers per root hertz or something like this. It's simply too noisy. So we have a second test mass, which is our witness test mass. If you think about it, this can be seen as sort of one of the LISA arms separated by millions of kilometers normally, these test masses, brought down to a separation of a few tens of centimeters, 38 centimeters here. And so by putting both of these in free fall, you can measure the relative motion of these. And so if you believe that there's no common mode, and we have good arguments why we think there is no common mode acceleration, then the differential acceleration is a good proxy for the individual acceleration. Again, if you assume things like both test masses behave the same. Now, it turns out you can't actually do that. You can do that on LISA. You can do it on LISA because one test mass is measuring along this axis and the other test mass is measuring along another axis, which is 60 degrees away. And those are not degenerate degrees of freedom anymore. They are separate, so you can make a spacecraft follow both of them, okay? And you can see that easily if you just change that angle to be 90 degrees. I don't have a picture of that, but if if your test mass 1 is measuring here and test mass 2 is measuring here, it's very easy to see that you can translate your satellite to follow both in 2 degrees of freedom. And that's no different if it's 60 degrees. When it becomes different is when it goes to 0, right? which is the case in LISA Pathfinder, you can no longer follow both of these test masses with one satellite. Eventually one of them will hit the walls. So what we have to do is apply a little bit of force to the second test mass using electrostatics to make it below band, below at really low frequencies, to make it follow the constellation of the spacecraft and test mass 1. Okay. And here you see also how the drag-free works. So you see two measurements here interferometrically, and I'll talk about these in a bit more detail. The first one is to measure how is the satellite moving with respect to the test mass. That's identical as we do on LISA. And then I control the spacecraft by firing these little thrusters to make sure the test mass doesn't hit the wall. The second one is made by measuring the relative position with respect to the first test mass and controlling that to be fixed. Okay, so I have this sort of witness test mass, and because I know what force I've applied on the test mass, I use that in my inference of the differential force that's acting on the two, and we'll see that a bit later on. What are the characteristics of this? Well, so it's at low frequency. The measurement band is, you know, around the millihertz here. Experiments take a long time, so we have data sampled 10 hertz or so, less often. And you know, single injection sine waves take hours before you get any reasonable signal to noise. So these experiments take a long time. And when you look at those frequencies, you realize that 3 months isn't very long, actually. You don't fit many cycles of a millihertz into 3 months of time. So what else do we have? We have 3 bodies that we're controlling. All the 6 degrees of freedom of 3 bodies have to be dealt with. The spacecraft here is something around 500 kilos, 427 kilos, and each test mass is almost 2 kilos. So they require significantly different actuation, and I already talked about that. So we have 18 degrees of freedom that we have in play. We control 15 of those degrees of freedom. We leave the linear degrees of freedom of the spacecraft effectively uncontrolled, so we don't control the orbit of the spacecraft, only its pointing within the orbit. One of those degrees of freedom, of course, is our drag-free one. It's the one that in LISA is the x-axis of the test mass. It's the measurement axis. The sensors that we have, we use different ones for different degrees of freedom and different frequency ranges. It's a complicated hierarchical sensor scheme. We use, starting at the lowest frequency, we use star trackers for the spacecraft angles. We use interferometry for the longitudinal motion of the test masses, as I've said, but you can also use the interferometry to measure the tip and tilt of the test masses with respect to the optical bench, so 2 test mass angles here. And then for the other degrees of freedom, we have capacitive sensing. Actually, we have it on all degrees of freedom, though it isn't as sensitive, so it's only used on the degrees of freedom where we don't have interferometric measurements. This is what a star tracker looks like on LISA Pathfinder. So they really look at the stars. You take a picture of the stars, you compare that to a star catalog, and you figure out where you are and which way you're pointing. Okay, and you do that on different axes, and you figure out where you're pointing in inertial space. It has a pretty low accuracy compared to the other measurements we make, but it's good enough to control the spacecraft at low frequency. Here they are mounted. There are 2 of them for redundancy. Everything is redundant in space. Mounted here on the satellite just before one of the ground tests. The optical metrology is done a little bit differently from what I talked about yesterday, though the phase measurement is rather similar. We use something called a Mach-Sender interferometer, so we take a single beam, we split it, and we send it around 2 different paths, and then we interfere that again and measure the relative beat. And as we saw yesterday, the phase is then encoded in that beat, and I'll talk through that a little bit more detail in a moment. We measure these relative positions, and we measure these angles. I already mentioned this. I can skip through a little bit quicker to show you what it looks like in a sort of a CAD drawing. Here's what the 2 test masses look like here. We have beams injected onto the optical bench through fibers, and these beams are then moved around on the optical bench to form these different interferometers. Okay. All of them together produces a pretty complex optical layout with multiple photodiodes, all of which we were using extensively to do the measurements and to understand the noise here. I'll go through a little bit more what they do in a moment. The inertial sensors are effectively bridge capacitors. We have a set of electrodes surrounding the test mass on all sides, and we read out effectively a capacitive bridge here to tell us where the test mass is in that housing. Okay, it has a rather higher sensing noise, roughly nanometer per root hertz compared to picometer per root hertz for the interferometer. So you can't use it for the main measurements, but you can use it for the other measurements. We have actuation two types primarily. One on the spacecraft using micronewton thrusters. They can do something like up to 100 micronewtons of thrust, but they do it with micronewton accuracy. Okay, and then we're able to do also actuation through electrostatics on the test mass using the same electrodes in all 6 degrees of freedom, and that can be of order micronewtons of force, but with really high resolution, so with femtonewton accuracy. So how does this all work in total? So we have those 3 bodies, 2 test masses in a spacecraft. You have to look at the dynamics, the equations of motion of those 3 bodies. The motions of those can be expressed in terms of meters and radians with respect to some inertial frame. You use sensors to measure those quantities. Those sensors give you estimates of those quantities. You then feed those into a control system which produces a set of forces and torques which applies to your actuators. Those actuators then translate those forces and torques into real forces and torques on the bodies, and that produces dynamics. And you do that to keep that whole system stable in the way that I described before. So that's effectively how that works. In a little bit more detail, this just picks up on the previous slides. We have in the control part something called the drag-free and attitude control system. So that takes this combination of different sensor readings and effectively then controls those 15 degrees of freedom of the whole system. So we have the star tracker, we have the OMS and its data management unit, which produces all these measurements, and we have the inertial sensor subsystem, which produces a bunch of delta capacitances, which have to be calibrated to give us the displacements and angles that we want. We then have this drag-free control system, which is a big computer program effectively. Those sensor outputs are all processed, partly to calibrate, partly to decorrelate or rotate them to correct for any kind of misalignments. And then there's a sensor mapping scheme. We have more measurements than we need, okay, because there's redundancy between these 2 systems, and so you have to make a choice of which measurements you use for which degrees of freedom. Then you take a set of control matrices, a set of filter functions, if you like, which convert those into accelerations and torques per unit mass, per unit inertia. You decide where you're going to apply those onto which actuators and around which degrees of freedom, and then you send those off to different actuator algorithms. It's fairly obvious, I think, that with, for example, with a thruster, a micronewton thruster, you can only push, you can't pull, you can't suck the gas back in or something like that. So you can only push. So if you want a spacecraft to go that way, you fire that thruster, and if you want it to go that way, you have to fire that thruster. So there's an algorithm that goes along with that. And this all goes through different control units, different sets of electronics, and eventually makes that control system all close out. And we have the dynamics. So this is a little movie of what that looks like. We have 2 test masses in free fall, following, in principle, perfect geodesics. We put an optical bench in between. We make these interferometric measurements that I mentioned, and we're able then to back out the relative motion of these 2 test masses, and therefore estimate the differential forces that are acting. To show you some hardware pictures, you start with a laser unit. We have to modulate the laser light, as we'll see in a moment. We combine all those different beams and measurements on the optical bench. We make phase measurements of those optical beats, and then we process those signals to produce real absolute measurements in terms of meters and radians of angle. So a little bit more detail then. We start with a very low power laser in Laser Pathfinder. It needs to be only a few tens of milliwatts. It's the same wavelength as we will use in LISA. We send that light to a beam splitter. We split it into two parts. So this light has very common properties. It has the same frequency noise, so we don't have the problem that we had we saw yesterday in laser, where we have two different sets of frequency noise, so a high frequency noise coupling. Here it more or less is cancelled by design. Okay, we then frequency shift those two beams with respect to each other using acousto-optic modulators. We shift them by this one by 80 megahertz plus a delta, and this one by 80 megahertz minus a delta. That's just for technical reasons, the way these modulators work. And that means the difference between these two optical frequencies now is a kilohertz. Okay, and so I'm going to take those two different frequency beams which have common frequency noise, assuming we don't add any, and so I'm going to transport those onto an optical bench. One of them I'm going to reflect off the test mass, such that the phase of this light is influenced by the motion of the test mass, okay, and that's our signal. The other one I'm going to let carry on. I'm going to combine the two and make this optical beat signal here, measure the phase of that at 1 kilohertz, and use that to measure the test mass motion, okay. So here in the system as we had it, something like 1.5 nanometers results in a degree of phase change. We typically measure microradians of phase change, okay, because we're measuring picometers. Then those raw phase measurements are used to produce our longitudinal and angular measurements, just using a relationship to the wavelength or differences of phase for the angles. That's shown here. There's a control computer that does all of that. So just to run through the interferometers, because we have more than the two that I've mentioned. I've already mentioned this one, which talks about, which measures the motion of the bench with respect to the free-falling mass. We have the other one, which measures the relative motion of the two masses. In principle, to a very high accuracy, motion of the bench doesn't appear in that interferometer. It's not entirely true, but broadly speaking, you can see that it doesn't. We have another interferometer, which is all contained on the optical bench, doesn't touch any of the test masses, and that's our reference interferometer. So that measures the phase fluctuations on the light coming in off the fibers, because that's going to be a dominating noise source in the other measurements. So I can subtract it, because this one doesn't include the quantities I'm trying to measure. And then I do actually have to control the frequency noise a little bit, because there is some residual frequency noise due to the fact that I can't build these path lengths completely equal. So we deliberately measure the fluctuations of the frequency of the laser and use that to stabilize the frequency of the laser in a control loop. Okay. Here's just a nice picture of what that looks like. This is the optical bench. You can see some photoreceivers here which measure those optical beat signals. That's the vacuum can, which inside it has a little optical window there to get the beam in. Inside you can see the front surface of the electrode housing, which has a hole which lets the beam go through, and that through there is then the test mass. Okay, so we interrogate the test mass through that little hole. Okay, and then that's put all together like that. You can see here some of the optical powers. We're typically hitting the test mass with something like a milliwatt of optical power, and that in itself is actually a source of noise, which we'll maybe touch on later if there's time. Okay, so we talked already about noise performance in laser and what noise effects limit our ability to make the measurements we want to do. You can do the same for Laser Pathfinder. We did that extensively, both in designing the mission and as we developed the mission. We kept this up to date to understand where we think the performance would be when we launched. This is a snapshot of what it looked like just before flight, what we understood from ground measurements, from further advanced modeling that had been done, and so forth. And you see that there are a number of interesting features here. First of all, this was the requirements that we had to build against. Okay, you can see that our estimate is significantly lower than the requirements, and that's not too surprising. When you begin a mission that takes 10 years to develop, you're usually conservative in all of your parameters, such that you're sure you're going to meet the requirements. And of course, being conservative, you know, a few times out of 10 you get lucky and things are better than you designed them for. and you get a lower noise level here. So this noise level is made up by lots of different things. There is a bunch of things associated with thermal effects, primarily fluctuations of thermal gradients. We have effects associated with magnetic fields. The test mass is more or less amagnetic, but there is still remnant magnetic moments in the test mass, and so any magnetic field gradients can have an effect here, coupling to the spacecraft. We have an effect which comes from pressure. The test mass in its housing is actually evacuated, so that electrode housing and the vacuum can is evacuated to outer space, which is a pretty good vacuum pump. Okay, but nonetheless there is still gas in there. There are residual molecules. We're at something like micropascal, I think, at the end of the mission, but that means there are still molecules in there, and they hit the test mass, and that's a force noise. That's a transfer of momentum. Okay, so there's an effect of pressure. There's a primary noise source here at low frequency, which comes from the fact that we have to actuate on that second test mass. Now, I said it was at low frequency, and that's true, but whenever you have to actuate on something, you can never do that as stably as you would like. So we have to do it by applying voltages, and you cannot produce infinitely stable voltages. Those voltages fluctuate, and those fluctuating voltages produce a fluctuating force, and that ends up as a noise here coming from the actuation. And as we talk through some of the results, you'll see that was a pretty key parameter in the success of LISA Pathfinder. And then up at this end here, you see the sensing noise. We had done a lot of measurements on ground of the performance of the optical metrology system, and this was where we thought we would be. You'll see also that we were wrong in that. It was expected still to be better than what we were designing for, but it was at the level we needed for LISA, but we actually did a lot better. So if you talk about OMS sensing noise, there are a number of things that play a role here. Things like the shot noise is in there, though for LISA Pathfinder it's very low because we have enough noise, we have enough laser power. There's electronic noise of the photoreceivers that's important. There are things associated with analog to digital converters to make these phase measurements. There is some effect of frequency noise. We never get that perfectly away. And there is also effect due to the relative intensity noise of the laser, which can couple also to the phase measurement. However, even though we did all that, we managed in flight to do rather better than we were able to do on ground. So this busy plot shows 3 traces. Let's see, we'll go from top to bottom. This red curve is done on ground in a test setup, but with no test masses, so with fixed mirrors in place of the test masses, but fixed is relative. Okay, so fixed on ground isn't really very fixed. They still move around and are still reasonably noisy. So at low frequencies they are certainly moving around. We have an amount of noise here that we can't completely explain on the ground, it's fair to say. The contrast in the interferometer, which is sort of a measure of how well those 2 beams overlap each other, was pretty high, but not as high as we achieved in the end in flight. When we went to orbit, we immediately made another measurement, which is a similar condition. However, this time the test masses are in place, and the grabbing of the test masses was not done in a way such that they were properly aligned for the interferometer. They were just grabbed where they were. Okay, so that's a very low contrast measurement, but it shows a similar kind of noise level to we saw on ground. Now in the end though, when we released the test masses and properly aligned them, the contrast in the interferometer went up to 99%, so almost perfect, and the noise performance was very good, so it was significantly better than what we were able to do on the ground. And we don't totally understand that. We understand this noise level very well. We didn't ever understand these noise levels very well. Actually, the grabbed one in flight we do understand. The red one we don't totally understand what was limiting us on the ground. It's probably a combination of vibrations, acoustic and micro vibrations and things. It's important when you look at these kind of measurements of a performance of a sensor to distinguish signal, what it is that sensor is measuring, from the performance of the sensor itself. So this is the sensor noise here. All of this other stuff in green is actually the test mass motion that you're actually trying to measure. Okay, let's talk a little bit about the Pathfinder science observable, the quantity that we were tracking and the quantity that we used to understand the differential acceleration on the test masses. So again, we were trying to obtain this quietest possible differential acceleration of two test masses. This gives us an assessment of the residual forces, and that's what we need to know for LISA. Okay, so the way you do that then, this is this quantity here, the residual differential test mass. It's related to the second derivative of the relative motion of the two test masses, so that's x12 double dot. Okay, so that's the in-loop acceleration of the two test masses. Remember, we control one of them. But I know what those control forces are, or control accelerations, or force per unit mass. So I can subtract that away to look at what are the residuals. In LISA, we don't control, so this is not relevant for LISA. So I take that away. I have two other quantities which you can argue are relevant for LISA to some extent. So we, depending on how we look at this, we either include these or subtract them. These are force gradients, so sort of stiffness terms. These are negative springs, if you like, with units of per second squared multiplied by a displacement gives me an acceleration. So I have both one spring which is related to the environment of test mass 1, and a second spring which is the difference of the environments of test mass 1 and test mass 2, and they couple slightly differently. Okay, I've just said all of that. Now, this control force we sort of know, okay? We know what we asked for. We know what we commanded. We don't actually know what was applied. Remember this little picture from before. What we do know is this quantity here, which is the amount of newtons and newton meters that we tried to apply to the system, but we don't perfectly know the actuator, and so we don't perfectly know what forces and torques were applied on the bodies themselves. So this G control is actually a function of the thing we commanded plus some unknown parameters like a calibration gain, maybe a delay, things like that, and we have to fit that out. We have to calibrate that in order to do this properly. And we do that with something called system identification. So this is identifying parameters of the system. So how do we do that? These are key things. At the beginning, when we start up, we don't know very much yet. What we do know comes from what we did on ground in terms of measurements, what we're able to do by modeling the system, which is not too bad for a system like this, plus the results of any of the industrial commissioning that was done in flight. So we knew a little bit before we started. The rest we do through dedicated investigations in flight. We do experiments. Here's an experiment. So the goal is to understand in particular the gains of those actuators, okay, so that we can back out the control forces. So what do? So you inject a signal here into this measurement. Okay, this is the measurement of the, now let's see, which one is it? This is the measurement of test mass 1 with respect to the spacecraft, or vice versa, it doesn't matter. And we inject a signal there, so we try to make the spacecraft follow this signal. Okay, it's like an artificial signal appearing in this measurement. The spacecraft tries to follow it by firing the thrusters and applying a force on the spacecraft, and this is the commanded force on the spacecraft. Okay, and then we look at what we actually observe. Does the spacecraft actually follow the thing that we asked it to do? Do we observe the thing we commanded? And the difference between those two things tells you something about those parameters of the system. There's another measurement, of course. We have a measurement of the relative motion of the two test masses. Nominally speaking, if the spacecraft moves and the test masses don't, you would expect this signal to be 0. That's not true because nothing is perfect. And so that residual motion also tells us some information about the system, and we can get out some other parameters from that. There's a second part to this, which is I can deliberately force the test masses to oscillate with respect to each other through another guidance signal here. and I can look at what force gets applied on test mass 2. And again, the difference of these two things tells me something about that actuator primarily. Okay, and so I look at this residual here and I get something out. I don't see anything on the spacecraft, of course. The spacecraft is far too noisy to measure any kind of back reactions from forcing the test mass. Okay, so if you draw a sort of control diagram, and I don't expect you to follow this immediately, but you can see things like the spacecraft dynamics here, the two test mass dynamics. We measure through interferometry the differences of these different dynamical responses. These are associated also with spring terms, these force couplings, with parameters associated with delays, and with the properties of these two actuators. And so those are the things we try to get out of this, okay, by doing these different experiments. So here's real data. This is data from an experiment done in flight, okay, and it's always nice to look at units and these kind of things. You see here the time scale of the experiment is minutes, a few hundred minutes long. Here the amplitude is nanometers, okay, so we made let's see, x1 is the blue curve, that's the spacecraft motion with respect to the free-falling test mass. We made a 427 kilo spacecraft oscillate at nanometers, which is quite a brain-bending thing to think about. But we're able to do that, and we're able to measure it, and more importantly, we're also able to measure the relative motion of the test masses here because the noise in the interferometer is so quiet. Okay, so then the analysis of that experiment follows that same observable equation that we're trying to calibrate, but the coefficients in here are now parameters of a fit we can do to the observations, okay? And if you get this right, if you can explain the observation with respect to all these other parameters, then you should have no signal left in your residuals, okay? And I'll show you how that works. So our observation is the second derivative of the relative motion of the test masses, and our model to explain that motion is these other quantities here, okay, with their associated parameters. And once I get those two things to agree, all of my injected signal goes away, and I'm left with the residual noise. This is the observation in the frequency domain. It doesn't make too much sense in principle to look at frequency domain for an injected sinusoid, but it gives a sense of what's going on. So all of that is signal power coming from the injections we made. If we account for our best estimate of the control forces, we subtract quite a significant amount of that. So in removing that noise power, we've tuned the parameters of this control force. We've calibrated the gain. Okay, I can do the same for another parameter here, and you see there's very little difference. So we're not very sensitive to the parameter involved in that force gradient. We are, however, more sensitive to the parameters involved in the second force gradient, and we calibrate those well. And you see we're left with something which is noise only, and I was remiss in not showing you the same spectrum when we don't inject signals, but believe me, it looks just the same as that green thing. Okay, and then we're able to measure these parameters. I didn't talk about them in too much detail, but these are they. You see that we measure them with quite high accuracy, even though we're only injecting nanometer type signals. And so we can pull those parameters out with proper posterior distributions and so on, and use those to calibrate the system. And so now what we do is measure noise only. We don't inject anything. We're asking ourselves, what force noise is impacting on the test masses, and this is my measurement of it. And since I now know these parameters, I can construct this observable from the data that we measure. Here's the first one. This was 40 hours of measurement just after the spacecraft was handed over to us. At the time when we started mission operations, our requirement for LISA Pathfinder was still this one. The old requirement for LISA was down here. That's since evolved based on the Pathfinder results, but we used to be somewhere down here. And you see that already, as soon as the thing was switched on, we were making a measurement that was significantly better than all the requirements. And you might remember that this looks rather similar to that theoretical plot I showed where we were actuation limited down here. Okay, So this is a little higher than we predicted, but it's in the ballpark of where we expect it to be. This flat part, and okay, maybe you have to squint a little bit to believe me that that is a flat piece of noise. It does suggest that we were limited by pressure, and you can calculate roughly the pressure we expect it to have and what force noise we expect, and they come out roughly right. Up here, this was a very strange bump of noise that we didn't have any real clue what that was at the start. That was an unexpected feature. I'm going to talk about DC forces for a moment. I talked about this actuation earlier on and said that that's an important and limiting noise source, and it's something that to a good extent doesn't exist in LISA along the main measurement. But because we have to control the second test mass in LISA Pathfinder, there is an actuation you have to apply if there's any DC relative force acting between the two test masses. For example, the fact that there's a big lump of optical bench in between, a big lump of 20 kilos of glass between the two test masses, pulls them together as a DC force, a gravitational pull. On the ground, we try to balance that with other masses outside on the other side of the test masses. Okay, so I have my 20 kilos of optical bench here. I have a test mass and a test mass. They're both pulled in, and so what I do is put other masses here, which I think were something of order a few kilos, maybe 2 kilos here and here, with the idea that I balance these DC forces, okay, so that I get zero. I have no pull in that direction on the test masses. Now, if you don't get that right, the test masses will drift towards each other or away from each other, okay? And that's pretty hard to calculate on ground. Actually, to do that, they had to measure the mass and position of everything, including every cable tie, including every cable. The bits they cut off the cable tie were weighed and subtracted. I mean, they measured everything to calculate through a model what these masses needed to be and where they should be placed. And they did it pretty well, but still there's some residual there, and that residual has to be compensated by electrostatic actuation. And as I said, the electrostatic actuation is noisy, and so that's right. Yes.
Is that being considered though? Like you could imagine that if you didn't have it just right, if you had like a little stepping motor or something that moved a bit.
Yeah. When you're talking about femtonewtons, nobody likes things that move, right? Because you think it's not moving when it's switched off. The other problem you have is to do something that moves, you need space to do that. You need an actuator, and so you'd have to be further away from the mass, probably. And then you need more mass. It's falling off with R squared or something here, right? So we tried to keep lumps of mass as close as possible to the test mass and as accurately as possible. Turns out for LISA that's not as big an issue as it was on Pathfinder, because we don't have this problem of the test masses falling together. It does create an orbital disturbance, if you like, because we chase the test mass all the time. But it's the bigger deal is that you don't want any torques on the test mass, because in LISA that's a force noise as well. Okay. Yeah, so we get more actuation noise the bigger this differential DC effect is, so that was important. So remember at the start, this was our best estimate of what they had done. In other words, it was based on the error they had in calculating the position and mass of these two balance masses. Okay. That's what I just said. But before we flew, we had no idea how well they had done. Obviously, they were aiming in construction for 0, but the error we didn't know. Okay. So we switched on and looked at the time series of the relative acceleration of the two test masses, and we have this strong drift. Well, the drift is one thing. Let's ignore that for a second. But the actual sort of DC level is pretty low. This is picometers per second squared of DC residual acceleration here. So they balanced those two test masses to picometers per second squared. Okay. Or piconewtons, if you like. Now, we had designed the system to operate with something like nanonewtons of differential force, not piconewtons. So we were able to turn down our actuation authority by quite a lot. Okay, we were using less than 50 piconewtons, so we could reduce it. And in reducing that to some lower level, and we're always conservative when we do these things, that reduces the voltages, the size of the voltages used for the actuation, which in turn reduces the voltage noise because they scale, and that in turn reduces the force noise, which goes as the square of the voltage, right? So we did that, we did it in flight, we reduced that, and we saw the noise go down here. But it didn't quite go down as much as we had hoped. We still had some excess down here. So we did another run, we reduced again the authority, and some more time had passed, and the noise went down. And so, you know, when you're doing these things under high pressure, you start to construct a scenario in your mind where you're actually doing something. It's not always true. So you change things and things happen and you think they're causal, and they aren't always causal. So that's a lesson when you're doing experiments. You always have to repeat things. For a while we addressed this noise bump. I'll just talk about this briefly. We'd figured out in the meantime that this was coming from crosstalk of the spacecraft. So the spacecraft moving around produces cross-coupling on the test mass. Have I got a picture of this? I do. So the easiest one of there are many different terms here, but the easiest one you can see is, okay, you'll appreciate that there's no difference in a relative motion measurement whether the test mass rotates or the bench rotates. Those two things are the same, okay? So if my beam hits the test mass, it's already off-center in the sense that the reflection surface is away from the center of mass here. But if it's off-center in the other degree of freedom as well, there is a direct coupling into the phase measurement from the angular motion of the test mass. So I have a fake longitudinal signal, okay? And that's what that was coming from. It's actually spacecraft motion driven mostly, but you can see it in this simple picture. So we tried to understand that. We did a lot of experiments where we oscillated the spacecraft in different degrees of freedom. You can see them here. We moved the test masses around and oscillated some more. And we tried to build a model of all of that to understand how to move the test masses to reduce this. And we were partly successful. It turns out it's much more complicated than we had thought it would be. We sort of did it on the fly under real-time pressure with pen and paper and calculated some numbers and some new offsets for the test masses. And, you know, we did not too bad. We got some of it away, but not all of it away, okay? So we had to do a lot more work to do that. In the end, actually, it turns out it's easier to do it using measurements of these angular motions and just subtracting them. You can do that a little bit better. The reason why you prefer not to do that is the measurements of the angular motions are also noisy. They contain measurement noise, and the measurement noise is not coupling through this. So when you use measurements to correct it, you add measurement noise back in. And so that's why it's always better to do things in hardware if you can. Okay, come back to this drift. This is a slightly different scale now in femtometers per second squared now, but you can still see this is our full measurement here. This is our delta G, our residual acceleration measurement. You can see it's very quiet. You can't see the noise with respect to this drift, but the drift is quite large, okay? And that's almost entirely driven by the fact that we're throwing away cold gas to thrust the spacecraft around, okay? So we're losing mass, and that changes the distribution across the satellite of the DC forces acting on the test mass. And so we could actually control that by using mass from different tanks. We could use the gas from the different tanks and control whether this drift was negative or positive, and so we tried to keep it around 0 in the end. Okay, so we were left still with the question of what is this low frequency noise? It was not in our model. We had no prediction for what this was or where it could be. You start to see now though that the white noise part here is much more distinguishable now that we've got rid of the bump and reduced this part a bit. We realized there were some other effects that we hadn't taken into account. This hadn't been thought of on ground before, but we actually have a measurement system here which is all effectively on the optical bench, and it's jittering rotationally with the spacecraft. So we have a rotational measurement system, okay? So our measurement is made in a rotating frame of these two test masses. So we have all the pseudo forces that go into that, and we hadn't estimated those before, and we had to do that in order to explain some of the low frequency noise, okay? So when you do that, you can correct for some more of that noise. Now the effect of that noise, or the contribution of it, depends on where you are in the orbit and on the rotation rate of the satellite. There's a DC rotation to keep the satellite pointing at the sun and at the Earth, and that changes with time. In LISA, we will have this to some extent, but it'll be much quieter, because the angular control of the satellites is done using the interferometry, whereas here it was done using those noisy star trackers. Okay. So we could subtract a little bit more noise. Then we did another long run. It was endless long runs of collecting data, and we started to see new things that we hadn't seen before. You see these glitches and strange bumps and what have you. I'm going to look at this piece of noise where it's quiet, just for the purposes of discussion here, but these things are an issue. If I zoom in on one, this is a glitch of force, okay, in the femtonewton regime here. So we don't know what this is yet. These are an issue. We can talk about that later. But if you look at the quiet piece in the middle there, we are significantly better than we were 2 weeks before, but we hadn't really done anything. Okay, so that's always a little worrying when your system is changing and you haven't done anything. So in the end, then, if you look at that over the whole duration of the mission, and I'm going to say a little bit about what we think is going on here, we were able to go from where we were in April down to where we were at the end of the mission, like this. Okay, so you see the reduction in the midband, where the pressure continued to drop throughout the whole mission. You have fluctuations at high frequency due to the way that we do these subtractions using the other degrees of freedom, and also slightly due to the performance of the interferometer, which has a slight variation in noise performance. At low frequency, there seems to be a reduction, okay, over time, but we haven't explained that yet. So we have this low frequency tail, we have this Brownian midband, this one, which is all due to the residual gas around the test masses. It varies with temperature, as you would expect, because the outgassing changes. Here's just a nice plot from the first few days of the mission that shows this in action. This is the delta G, the residual force noise, as a function of time. You see it decays. This would typically be an exponential decay if you do this sort of pumping. We don't quite have that because we also did some other things with the temperature. First of all, some other equipment was switched on, the temperature went up, and then we lowered the temperature by turning off some heaters, and so we were able to lower the pressure around the test masses and reduce that noise. This low frequency tail looked like it was improving. I just showed you that results plot across the whole mission. It looks like it's improving, and that confused us a lot in the early days. Turns out it comes back to this whole story of being able to estimate the actual forces you applied on the test mass, not the things you think you applied. And we were fooled for a long time, and it took us a good bit of thinking to understand that we were not properly modeling that actuator. It's one thing to calibrate it, but if your model is wrong, that doesn't help you a great deal. So now we know how to do that properly, and it came down to looking in detail of the implementation of the electronics. There was some quantization noise in there that we needed to be able to model, and it was a function of the DC force, so that's why it was varying with time. We needed to put that into the model in order to do this properly, so it took a little bit of time. And then we fully reanalyzed everything, and we ended up with this plot that was published relatively recently, which shows the difference between where we were in the first publication compared to where we were by the end of the mission. And this time included in this plot are the LISA requirements that were derived from what we'd been able to do in LISA Pathfinder. We set new requirements when we put the proposal in for the mission, giving ourselves plenty of margin here for a reason I'll talk about in a moment. So this is still interferometric sensing noise, 100 times better than on ground, but it's the limiting thing over here. This part in the middle is still due to residual gas around the test masses and would still continue to decrease if we were still measuring. And this is partly known, okay? There is still some residual actuation noise coming from the fact that we have to control the angle of the test mass. That gives us a force noise here in a crosstalk. there's a force noise that comes from the fact that the laser beam that hits the test mass, its power is not perfectly stable, so it produces a momentum transfer as the number of photons or as the power fluctuates. Okay. There's a few other things in here, but partly we don't know what it is at the moment. So we have a few hypotheses for what other noises we have in here, and we continue to refine the models of these other noises to try to explain more and more of this, but that's ongoing work. This shows you roughly where we are. These are things that we know about or have estimated through direct measurements in flight, and you see that the total of what we explain in black here doesn't quite meet what we measure. It's not far off, but it's not as comfortable as you would like it to be, so we have more work to do. And that's partly why also then we have some margin here on the laser specification to allow for this unknown to be slightly different than what we got in Laser Pathfinder. Okay, I just have a few more slides. I'm going to try and bring this into context now for LISA. Are there any questions up to this point before we talk about what this means for LISA? Yeah.
It looks like most of the noise and other frequency is actuation noise that is due to the fact that you have to control the two bodies. I mean, one of the two bodies.
Yes.
But this is not an issue with Lisa.
Yes, that's true, but it's 2 degrees of freedom. One of the degrees of freedom we do have to control in LISA, but the longitudinal